So now let's talk about higher order derivatives. So we're going to think about this in the context of a real world situation. So for example, you have some kind of object moving, and then you have a function to describe its position. I'll call it S of t. This is the position function. And so then you can take the derivative of this function, S of t, but then the function you get is the velocity function. So this usually gets renamed v of t. But then you can ask what happens when you take the derivative of this velocity function. So when I take v prime of t, I get the acceleration function. So usually this is called a of t for acceleration. And really what have we done? We started with a function and took its derivative, but then we took another derivative. So we've taken two derivatives. So this is written as s prime prime t. So once we take a derivative, we can take another derivative and another derivative after that and keep going. So just so we know the terminology that's used, the first derivative is the one we've been talking about, which we write as y prime or f prime of x or dy dx. Those are all ways we denoted the first derivative. The second derivative, we use two. When you take another derivative again, you use two marks there, or you could write the second derivative as d squared y dx squared. But you could take a derivative of that second derivative to get a third derivative. Y triple prime f triple prime d cubed y dx cubed. And you don't have to stop there. You can keep going. You can take the fourth derivative. But we get tired of writing those marks up there, so we would write y parentheses 4, f parentheses 4, or d4y dx to the fourth there. And this could keep going. You could take a fifth derivative, a sixth derivative, and so on and so on. So now that we know what these higher order derivatives are, let's look at doing an example involving them. So in 1971, an astronaut, David Scott, demonstrated that a feather and a hammer fell at the same rate on the moon. The position function for each of these falling objects is given by the function s of t, negative 0.81 t squared plus 2, where s of t is the height in meters and t is time in seconds. And what I want to know is, what is the ratio of Earth's gravitational force to the moons. Well, we're going to look at our position function, S of t, which was negative 0.81 t squared plus 2. And we're going to take the derivative of that. Remember, that gives us velocity, negative 1.62 t, using the power rule. And then we take another derivative, a second derivative, to get our acceleration here. And it would be negative 1.62. So this right here tells us everything we need to know about what's going on in the moon. On the moon, the gravitational force is this 1.62. So the acceleration due to gravity on the moon is 1.62 meters per second squared. But on Earth, we know on Earth it is 9.8 meters per second squared. And what I was asked to do was find the ratio of Earth's gravitational force to the moon's. So you want to do a fraction with Earth on top, 9.8, and the moon on bottom, 1.62, to get our ratio, which is approximately 6.05. So the gravity on Earth is about 6 times more than the acceleration due to gravity on Earth is about 6 times more than it is on the moon.